Now, I can start to try to think about superimposing. I've got only my axials here. What if I started to kind of put in or try to put in the equatorial positions? Right. If you have an axial up, that means your equatorial has to be down. Your substituents can't both be going in the same direction. I can't have an axial up and an equatorial up. Right? So if the axial is one direction, the equatorial has to be the other direction. So I have the axial up, and I just drew in an equatorial down. All right, go to the next carbon. We can see I've already labeled the axial down on this next carbon. So the equatorial here would have to be going up. And just around the ring. That axial is up, so my equatorial is down. All right, yeah.
Do you always have both in one molecule?
Yes. Yeah, all of these carbons, because think about it. I'll just take this carbon as an example, but it holds true for all the other carbons as well. That carbon is making 2 bonds to carbon, right? It's making a carbon-carbon bond there, that's 1. Making a carbon-carbon bond there, that's 2. That means it has, remember all carbons have to make 4 bonds, so it has 2 remaining bonds it has to make. In a 6-membered ring in a chair form, one of those will be the axial and the other one will be the equatorial. So all of those carbons in the ring are going to have an axial position and an equatorial position. Now, so like I said, it's usually when people are starting to draw these chair forms, it's pretty easy for them to draw in the axials. You just either draw it straight up or straight down. Where it gets interesting is when they start drawing in the equatorials. You see all sorts of weird things. An equatorial sticking into the middle of the ring, just weird stuff. And so there is a method to this madness, something that will maybe help you draw in your equatorials. When you're drawing your equatorials, what I want you to focus on is one of the carbon-carbon bonds. Right. And so if I'm going to look at this one for instance, I'm not going to look at the carbon-carbon bond that's directly attached to it. I'm not going to look there. Instead, I'm going to look to the next carbon-carbon bond. This one. Do you see how this carbon-carbon bond is parallel to that equatorial position? And it's saying that it'll hold true all around the ring. Look at this one, for instance. Okay, look at that equatorial position. So I'm going to compare this again, not to the carbon-carbon bond that's directly attached, but to the next carbon-carbon bond. Do you see how that CC is parallel, or it should be parallel to that equatorial position? Again, I could come in and draw that equatorial position should be parallel to that CC. So hopefully that kind of gives you a little bit of assistance in drawing in your equatorials. They tend to be a little bit trickier to handle, to get them to look right. All right. Okay. So this has all of the axials and equatorials drawn in. So all of the axials are red, all of the equatorials in blue. Now, one thing you need to get out of your head altogether is just because axial equatorial has absolutely nothing to do with cis and trans. Just because 2 things are axial does not mean that they are cis to each other. Just because 2 things are equatorial doesn't mean they're cis to each other. There is no connection between axial, equatorial, and cis and trans. So I want to show you what I mean by that. Have a look at the two di-substituted ring systems. We want to identify these two different dimethyl cyclohexanes as cis or trans. First off, let's figure out axial equatorial. What type of substituent is this methyl over here? Would that be axial or equatorial? Yeah, it's equatorial because it's not going perfectly up or perfectly down. So that would be equatorial. Would that be equatorial up or equatorial down? Yeah, that is equatorial up. So what about the other methyl group? Yeah, that's also equatorial and it's going down. So that's equatorial down. They are both equatorials, but they are not cis to each other. All right. Cis and trans has to do with the up-down thing. This methyl group is going kind of above the plane of the ring, while this methyl is going below the plane of the ring. They are going opposite directions from one another. And that is the definition of trans. Okay, despite the fact that they are both equatorials, they are trans to each other. The cis-trans has to do with the up-down thing, not the axial equatorial thing. Look at the other one. What about this methyl group? How would we call that? That's equatorial. And is it up or down? It's equatorial down. What about the other methyl group? Yep, that one is perfectly up. So that would be an axial, and that is pretty clearly going up. So here we're comparing, you can see you've got an axial and you've got an equatorial. That is not what makes that a trans ring system. Right, again, when you're trying to do cis-trans, we care nothing about axial equatorial. What you care about is direction. This methyl is going down below the plane of the ring. This methyl is going up above the plane of the ring, opposites. That equals trans. All right. Questions on that?
And so basically, because also following the patterns of how, like, for example, the equatorial ones on the one to the left. So since they're right next, sorry, the equatorial on the molecule to the left.
Okay.
Yeah, those ones. So since the two equatorials are next to each other, so they have to be opposite anyways. So that's always going to be trans.
Yes.
But if that methyl on the far left gets moved up one, then it would be cis. Because now it is
well, you're saying and keep it
well,
as an
sorry,
equatorial.
so, yeah, it's still equatorial, but then it's moved up to that.
Moved here.
Yeah.
Yeah. So if this so what would the equatorial be there? You would have an axial up, and then you would have your equatorial down. So if you move the equatorial methyl from where it is over there, it would be an equatorial down, which would be cis to that.
Okay.
Because they would both be going down in that case.
So that we can also identify whether it has a cis or trans configuration depending on where on the cycle.
Yeah, you can.
Okay.
I mean, that seems like more work to me,
Oh,
but
okay.
I mean, it's however you see it best.
Okay.
Yeah. Okay. So now the fun begins. Now that we've gotten all this established. As I alluded to earlier, you have just kind of one chair form. Both of those are the same chair form. These chair forms can actually flip. And what I mean by that is I can start taking this end, that foot, and I can bring it up to make it the head. At the same time, I can take the head and bring it down to make the foot. All right. What that, so kind of like that shows you. Notice in the left-hand structure, the head is to the right, the foot is to the left. In the right-hand structure, now the head is at the left and the foot is at the right. We just inverted the conformation. This is what is known as a chair flip. Now, I want you to notice what's happening to the substituents. In the left-hand conformation, in the left-hand chair, look at the head. Actually, let me go ahead and number these carbons just to give us some perspective. 1, 2, 3, 4. And I'll number the other one in the same way. 1, 2, 3, 4. All right. So basically all we did was, in going from one chair to the other, the one was the head in the left-hand form. We brought it down. So in the other chair form, the one is now the foot.
And now this alternates your equatorials and axials?
Exactly. That's the point. So look at carbon 1. In carbon 1 on the left chair, you had axial up, equatorial down. Look at your carbon 1. Look at your carbon 1 on the right. This has equatorial up, axial down. When you do a chair flip, all of your axials become equatorials and all of your equatorials become axials. On all carbons. Look at carbon, well, let's look at the foot. Look at carbon 4. Carbon 4 has axial down, equatorial up. Go over to the flipped form. In the flipped form, you have axial up, equatorial down. It happens all across the ring at every carbon position. When you do a chair flip, your axials become equatorials and your equatorials become axials. Does anybody have questions on that? Yeah, just when you do a chair flip, all of your axial substituents become equatorials and all of your equatorials become axials. All right, so I want to show you kind of how this happens energetically. So what you can see here is at either side of the energy diagram, you have the chair forms. Got chair form here, and you've got the other inverted chair form here. Now, what we're kind of looking at, I'm gonna blow this up a little bit, is in order to get from one chair form to the other, we're gonna start by raising the foot. All right, so I'm gonna start this conversion simply by taking the foot of this chair and I'm gonna start raising it up. And as you can see, as we start that motion, that's causing an increase in energy. As I begin to bring the foot up, that's increasing the energy of the molecule. And it's doing so because your intermediate is this so-called half chair. This half chair, what that is trying to show is that what used to be the foot is now in the plane of these other 4 atoms. So those 4 atoms, what was the seat, and now since we brought the foot up, these 5 atoms are all in the same plane as each other. And as we saw at the outset, anytime you have this kind of planar arrangement of atoms, that causes the eclipsing of all of the CH2s. So you have a lot of torsional strain here between those 5 eclipsing CH2 groups. Now that gets relieved a little bit as we continue the upward motion until ultimately you get to a conformation, or it's right at the center of what we call a boat. And that boat conformation looks something like this. It's like a chair that has 2 heads, like call it a chaise lounge. No, it's not a chaise lounge. It's a French word for that. I don't know off the top of my head. But anyway, this is not a great conformation either. You'll notice that the boat is significantly higher than the chair. And that's because you get a lot of eclipsing interactions from the seat. And then you also have these hydrogens that are kind of start kind of bumping into each other. All right. So that kind of formation of the boat is half of the journey of the chair flip. In the second half of the journey, we're going to start taking what used to be the head and bringing it down to become the foot. Now here again, it's kind of just the reverse process that we just did. Notice as we start bringing that this one down, we have to go through that super high energy half chair again, where all 5 of these atoms are in the same plane, causing all of that torsional eclipsing CH2s. And then we just continue bringing it down to where it ultimately becomes the foot. Now I have something on, sometimes it's easier to see this with video. I'm gonna switch to seconds. If you look on Canvas, there's a little cartoon video. You can see it's in the right there, the chair interconversion video. And it'll just kind of walk you through the various conformations. So this would be one of the chair forms. And then we're going to start kind of raising up the foot, and you can see it labels the different conformations. And we get to the other chair, and it just kind of repeats itself. So one Friday night, if you've got nothing better to do, put this on and enjoy yourself. But you might just have a look. Sometimes I found it useful to kind of like to pause at the various different conformations, just because it kind of helped me to kind of see it more 3-dimensionally. But yeah.
What are we supposed to like? What are we supposed to be like gaining like from this? Like, are we supposed to know like how like? Are we supposed to just be able to identify like which ones are gonna be higher energy, or are we expected to like what are we expected to memorize from this?
Oh, you're not going to memorize anything, but you should be able, well, I'll show you just right now. What you want to, ultimately what we're going to use this for is to predict stable conformation of a chair form. So, which is what we're going to talk about now. So if you're dealing with cyclohexane, it doesn't matter which chair form you're in, they're of equal energy. However, once you start putting substituents on the ring, that is not the case. One chair form is going to be a lot more stable than the other one very often. And so we can use that to predict what the molecule is going to look like the majority of the time. Remember, the molecule is going to spend most of its time in the more stable conformation. So have a look at this methyl cyclohexane. You'll notice in the left-hand chair, I've got the methyl on an equatorial position. By the way, what is the height? I have I didn't draw it in. I have a hydrogen there. Is that hydrogen going down or up? Yeah, it has to be going down because the methyl group is going up. So your axial position here would be like that, just for FYI. Once you do the chair flip of this, remember your axials become equatorials and vice versa. So if I draw the flipped form of this, what used to be equatorial up is now going to be axial up. Go ahead and draw in the methyl or the H group there as well. The H here would become equatorial. But notice the up and the down doesn't change. Right? The methyl group was up in that form, it's up in this form. Up, down does not change just because you flip the chair. Only the axial equatorial flips. Now, it turns out that once you start incorporating substituents on these rings, equatorial and axial is not of equal energy. It is much better to have your larger groups equatorial than axial. And that's because instead of picturing this as just a CH3, think about what that CH3 really is. It's carbon that has those H's bonded to it. And when you have these big groups in axial positions, they start sterically interacting with the other axial positions. Right. We call these 1,3 diaxial interactions. Right, because if I'm calling that one arbitrarily 1, that hydrogen that's kind of at the 3 position, that axial hydrogen is going to start interacting sterically with the big methyl group. Right? And same thing over with this axial hydrogen. So you start getting, when you have these large axial substituents, they start sterically interacting with the other axial groups. And you don't have that if that methyl is equatorial. If that methyl is equatorial, this CH3 is nowhere near that H in the 3 position. Okay. In addition, this is one time I will kind of show you a Newman projection of a ring. So this is the Newman projection of the methyl cyclohexane. Have a look at that ring carbon. So that would be the kind of 1 carbon away from the C1 as I've numbered it. So if we want to go ahead and continue numbering this. That would be carbon 5 as I've labeled it. That's a CH2 group. This has a methyl 60 degrees from that ring carbon. That 60-degree interaction is a gauche interaction. So not only do you have the destabilizing 1,3 diaxial interactions, but because this methyl group is 60 degrees from that ring carbon, that's also a gauche interaction, which is also destabilizing. The bottom line is, it is a lot better to have equatorial large substituents than axial large substituents. So let's practice this. This is what I'm going to expect for you to be able to do. I want you to draw the two chair forms of this molecule. And then I want you to predict what the more stable form is. So the way I would recommend starting these problems is just draw the molecule out flat at first. So I'm just going to draw a 6-membered ring like we always do. And now we've got to fill in, we've got to put in our substituents. I've got bromo on C1. Now, in theory, you could call C1 any of those carbons. I like consistency when I'm working problems of this type. So I always just start at the top. That's going to be what I call C1. And on C1, we have a bromine. So I'm going to go ahead and draw that in. And then on C2, we have a methyl. Now, is that the appropriate structure for this molecule? No, because I haven't indicated the stereochemistry, right? We're told specifically that this is a trans molecule. I haven't indicated that in the structure. So I need to show that. And again, the way we show that with these flat rings is simply with wedges and dashes. So I'm just going to go ahead and put bromine on a wedge, methyl on a dash. So that's showing trans 1-bromo 2-methyl cyclohexane. Now we're going to put this in a chair form, in 2 chair forms actually. Again, I would encourage you to be consistent with this. I always start, for whatever reason, like this. Then I'm going to go ahead and just draw the other chair form. Okay, so there's the 2 chairs. Now again, I like to be consistent. So I always start at this carbon. I'm going to call that my C1. I always call that my C1. In theory, you could put the C1 at any of those carbon positions as long as you get the right relative positioning of the other. But I always call that my C1, and I always start with an axial substituent. So I'm going to put my bromine axial up, and I'm calling that my C1. And there's no absolute truth to that. I could have put the bromine here or there or there or there or there, as long as you put the methyl right next door to it. But again, I like to do it this way because it helps me avoid personally making mistakes. So there's my bromo. Now I'm going to put the methyl right next door to it. I know it has to be directly next door to it because it's a 1-2 relationship. So if that's true, I know that the groups on that C2 are going to look like that. Go ahead and draw in the other. It's an H. where do you want to put the methyl? You want to put it up, equatorial up, or do you want to put it axial down?
Down.
Yeah, it has to go down because bromine and the methyl are trans to each other. Meaning one is up and one is down. That's what trans means. So I'm going to put the methyl group there. So that's one chair form. Any questions how we did that? All right, now we have to do the flip. I think I'm just going to go ahead and draw in my substituents, my possibilities, and then we can put in the groups. So that's the axial and equatorial at the 1 position as I've numbered it. And then you would have the axial and equatorial at the 2 position as I've numbered it. Weird bond angle. So where's the bromine on this C1 position? Is it equatorial up or is it axial down?
Equatorial.
Yeah, it has to be the same direction as it was here. If the bromine is up here, it has to be up there. Remember, the chair flip only switches axial equatorial. It does not switch up and down. So then when I go to draw in my methyl at C2, where does the methyl go? Is it axial up or equatorial down? Yeah, it's going down here in this form. It's got to go down in that form. Getting a little crunched up for space here, but oh, God dang it. It's probably just as well. That chair was not very good. Actually, I'm just going to start over. There we go. That's better. Okay. Questions on how we did that? Mm-hmm.
Okay, I see what's going on there. I was gonna ask, how did you determine that the methyl needed to go down is because its transit needs to be opposite of it?
Mm-hmm. Yep. And because the methyl group is down here, it has to be down there as well.
Be exactly one spot away.
Mm-hmm. Yep.
And we can place that spot anywhere, but it must be one spot away.
Correct. Yeah. So now the question is, which is better? Like the one on the left or the one on the right better? Yeah, I'm thinking the one on the left. Reason being, that's an axial substituent. That's an axial substituent. Once you do the ring flip, that's equatorial. That's equatorial. And you'll recall, as we just said, axial substituents are not nearly as good as equatorial ones energetically. You want to have your bigger groups equatorial versus axial. questions how we did that? All right, so I'm gonna give you one more. Got a couple minutes. We might not be able to finish this, but you can play around with it on your own. So we've got cis 1 tert-butyl, 4 ethyl cyclohexane. So again, I'm going to start by just drawing this as a flat ring. So 1 tert-butyl. And then 4 ethyl, and they are going to be cis to each other. So we're going to go ahead and start this by drawing the 2 chair forms. All right, so I've got my 2 chairs. Now I'm going to draw in substituents. And again, try to be consistent. I personally always make this my C1, and I'm always going to draw its substituent axial. So if I call that C1, I've got the tert-butyl, and I'm going to draw it axial. And then I come over to C4, and the ethyl group is cis. So if the T-butyl is going up here, the ethyl group needs to be going up there. In the flipped form, remember, up and down don't change. I drew my T-butyl originally up, which in the flipped form, it also needs to be up. Then on C4, the ethyl was originally up here. It needs to be up here as well. The last step, which one is better? In the first example we looked at, it was easy to determine what was better because both of your substituents were axial in one form and both of them were equatorial in the other form. Here, you're forced to make one of your substituents axial. Which one do you want axial?
One of the butyl, one on the left.
Yeah, we want, this one is going to be preferred. An ethyl group is a whole lot smaller than a T-butyl group. The one on the left is going to be greatly preferred.
Do you want your smallest substituent to be axial?
Yes, yeah. Okay, Oh, yeah,
Out
question?
of curiosity, what happens if on the off chance, there's like, let's say it's ethyl on both ends and then they are also, opposite, one's axial, one's equatorial, and they'll both just be the same. Pretty
Yeah, that would
much.
be of
Yeah,
equal energy and
okay.
that would spend equal time in the both chair forms. Mhm. Okay, so I think that's a good place to stop. I will see you in about an hour or so for the start of lab.